Welcome to our next lecture in this series on condensed matter theory. In this lecture I want to talk about Green's functions and how we can represent these Green's functions with the use of continuate fractions. A continuate fraction is in principle a complex number, but we will be able to use this for function as well, which we can write as a fraction, 1 over a1 minus another continuate fraction, 1 over a2 minus 1 over a3, etc., where the coefficients are all complex numbers. If we want to write down our Green's function in terms of a continuate fraction, then we should realize that this is a function of our frequency with a small imaginary offset, and then a real number b1 squared omega plus I0 plus minus a2 minus b2 squared omega plus I0 plus minus a3, etc. So also here we can write our Green's function in terms of a fraction with in the denominator another continuate fraction. And why we will represent our Green's functions like this will become clear when we discuss more and more examples and see how we can work with this. Any Green's function can be expressed in this form, or better said, any physical Green's function. We know that the integral of the imaginary part of our Green's function is equal to pi, and that's exactly the case here, whatever parameters you take. We know that the limit of our Green's function for the frequency to plus or minus infinite has to go to 0. Then we know that the poles have to be in the lower half plane of in the complex plane, which is definitely the case because we only have here a complex number that goes to 0. And then we have the Kramers-Kronig relations that relate the imaginary and the real part, and that's perfectly valid for any Green's function written in this form. A proof that all this is true is, or that indeed any Green's function can be written in this form, is not so hard, and it can be done with several of the properties that we will discuss later in this and other lectures. But once we've seen several examples where it works, the proof is not so interesting anymore either. So we will just state now that we can always do this. We'll show you for several cases that we can do it because we will find a form of this, and then the proof is not so needed anymore. So what do we use continuate fractions for? We are interested to calculate a Green's function between two sides. We generate a particle at r prime and we annihilate it at side r, which is given as 0 ar 1 over omega minus h plus I0 plus a dagger r 0. And we have, let's say, a finite Hilbert space with n sides, and we can write our basis of our Hilbert space as a dagger Ri out of the vacuum. So we have an n-dimensional Hilbert space. We can now have a look at a tight binding Hamiltonian. I here make an example of a one-dimensional tight binding Hamiltonian where this is the hopping And these circles are our sides, with some hopping parameters and some on-site energies. Then we have somewhere side R and we have somewhere side R prime. I'm now gonna divide my Hilbert space into two parts. I'm gonna say I have a part 1 or a part A of my Hilbert space, a subspace, and I have the subspace B. My subspace A is given by the elements A dagger R out of the vacuum and A dagger R prime out of the vacuum. It is a two-dimensional space. The subspace B is given by the rest. It is an n-2 dimensional space. If we write down our Hamiltonian as a matrix, then it is a matrix for A. It is the coupling between A and B, and matrix for Hilbert space B, and the coupling between A and B. We have a block Hamiltonian where this is in dimension 2 and this is in dimension n-2, a dimension 2, a dimension n-2. So the left top is a 2 by 2 matrix, this is an n-2 by 2, a 2 by n-2 and an n-2 by n-2 dimensional matrix. Now if you want to invert this matrix, which is what we need when we want to calculate the Green's function, then we can invert it as if it is a 2 by 2 matrix, where we just have to realize that the elements of our matrix now are matrices. So we want to invert a 2 by 2 block matrix, where the block refers to the fact that our elements are matrices again. And the matrix that we want to invert is not just the Hamiltonian, but is omega plus I0 plus times the identity matrix minus the Hamiltonian, which is your Green's function. Well, we can invert 2 by 2 matrices. This is 1 over omega plus I0 plus times the identity matrix minus HA minus HAB, 1 over omega plus I0 plus times the identity matrix now of dimension B minus HB, HBA. If you look at Wikipedia for inverting a 2 by 2 block matrix, or in the script you will find also the other elements, they are not so important. Because if we want to look at our Green's function, what we had here is the Green's operator between side R and R prime, then we should realize that both the creation of a particle at side R, or the creation of a particle at side R prime, or the annihilation of a particle at R prime, or the annihilation of a particle at side R, both bring you from the vacuum into subspace A, or from the subspace A back to the vacuum. So the only part to which we direct couple is the left top in our Green's function. So this is nothing more than starting from the vacuum, A dagger R prime, 1 over omega plus I0 plus minus HA minus HAB 1 over omega plus I0 plus minus HB, HBA, A of R to the vacuum. If you want to propagate through a system, then you create a particle at that side. Then you need to know the Green's function of that side, how you propagate in that. And now you can hop to other states. And then what happens is you hop there, and in order to know what the Green's function, what the influence of those states on the Green's function here is, you need to know how you propagate then in subsystem B. And that is exactly what you have here. You have omega plus I0 minus the local Hamiltonian, and then locally coupling to the rest. How do you propagate in the rest? And coupling back to your system. Or from the left to right, go from A to B, propagate in B, go from B to A. And what we see is that we already start to get something of the form of the continuous fraction that we had. Of course, this is just the first step. We can now do the same trick that we did for Hilbertspace B as we did for the full Hilbertspace. So we can define a subspace C. And the subspace PC is spanned by the states HBA, A dagger R prime out of 0, and HBA, A dagger R out of 0. This gives you two states, and you might have to orthogonalize them to the original state A dagger R and A dagger R prime. But we now say, well, you go from this state to the ones that you go afterwards, and then we can define a subspace D, which is the rest. So that is an n-4 dimensional space. And with this, we can, just as we did before, rewrite our Green's operator for Hilbertspace B as an Green's operator on the dimension of C, and how you couple from C to D. Within subspace C. So with this, if you now put this in there, you see that you can build up your Green's function in terms of a continuous fraction. We will not always need to go up to infinite order. I think I will show you several examples where you either go up to first order or to second order, and you can do a few more tricks here. But the most important part is that you can look at your full Hilbert space, you isolate a subsystem, and you see how you propagate in that subsystem, and you look at how this subsystem couples to the rest of the world. This coupling to the rest of the world is something that we call a self-energy, or in this case a self-energy operator, because this is not a single state but several. And the term self-energy is something that will come back in several other cases, and it tells you how the particle that propagates in your system, when this system is not the full system, is influenced by the rest or the environment to which it still couples. So what I want to do is have a look at a few examples to make this a bit more concrete, and then in the end we'll collect everything up and compare it to a few other methods. For now, thank you very much. We see each other later. Stay healthy.